All right. I will assume that we will have slides shortly for everyone to see. Those online, of course, can see the slides. But it is my pleasure to welcome Sanjay Reddy here to speak to us today. So Sanjay did his PhD at Stony Brook, and then he did postdocs at INT first, I think. And then we may have met there, but then at the CTP at MIT, the Center for Theoretical Physics, and that's where we first really started working together. After that, Sanjay went to Los Alamos National Laboratory, where he was a staff scientist, and he pulled me in to come over there. So then we worked together at Los Alamos for a while. And then Sanjay went to the Institute for Nuclear Theory in Seattle, where I followed again. So we overlapped an awful lot. And Sanjay is now the director of the Institute for Nuclear Theory. He works on a wide range of physics topics, and he will tell us about, hopefully show us also about neutron stars and measurements from LIGO, and how we're going to use that for, so we're just waiting for the system to reboot. Can you give an overview before we get your slides up?
Something good's happening.
Yeah. Okay, sorry about this. Thank you very much.
We'll see.
It started at number 13. That's not a good omen. Anyway, thank you very much for the introduction, Michael. It's very nice to be here. And I remember being here more than 10 years ago, and it's good to be back. So the story I'm going to tell you today is, thank you so much, is about compact objects, in particular neutron stars, and how they are finally living up to expectations. Since I think the 1930s, people expected these objects to exist. And in the 1940s and 1950s, a lot of people got excited about the fact that these are so compact that they're going to contain matter that's some few times denser than the matter inside the nucleus. And gee, that would be a great place to study new physics. But we had to wait a long time. We had to wait about 30 years till they were discovered by Jocelyn Bell in the late 1960s. And then we sent up a lot of satellites to measure X-rays and photons from these objects. And it's only now that we are being able to use them as laboratories. And the reason for this is the pieces of the puzzle that are needed to be put together to make them laboratories are finally coming together. So if you think about developments in theoretical physics, we now have a fairly sophisticated way of describing matter at high densities, and this is going to be a fair part of my talk. There are developments in astronomy and astrophysics where we can model, large-scale objects with complex physics inside it. And we also now have access to computing where we can run very large-scale simulations, including some that are being done here at Washington State. But most importantly, we need data. And until we have data to test our theories, we really are not going to learn a whole lot about neutron stars and what light they can shed on some interesting physics. So neutron stars are relevant to answering some very big questions. And these are big questions that have been in the nuclear physics and nuclear astrophysics communities for decades. We would like to know what happens to matter when you crush it to extreme densities. What happens to nuclei when you take them to densities that are much larger than what exists inside them? What is the physical mechanisms that power supernovae, neutron star mergers, gamma ray bursts, all of the very high energy explosions that we see in the universe usually have a neutron star at their core. So the central engine of most of the extreme phenomena in the universe are somehow related to a neutron star at the center. And very recently, we've begun to appreciate that understanding how the universe makes heavy elements, the most famous example is gold, uranium, platinum, all of these elements require extreme conditions to be forged. And neutron stars seem to be the only way in which you can make these heavy elements. And the big debate is, do you need one neutron star or do you need two neutron stars? And there are questions about dark matter. We know that some other form of matter that gravitates exists in the universe, but we've been unsuccessful in identifying any particle that could be responsible for this extra gravitational field that we see in galaxies and between galaxies. So neutron stars, the study of neutron stars and their observation can help us address all of these questions. And in this talk, I'm going to focus on question one: what are the states of matter at very high density? And if I have time, I'll talk about how you can use neutron stars to constrain some candidates of very exotic new particles that could compose dark matter. So the bottom line is, if we can measure and interpret neutron star observables, then we have a good chance of answering some of these questions. So for a nuclear physicist, this is kind of the holy grail of dense matter physics or QCD physics. We want to know what is the phases of matter at the most extreme temperatures and at the most extreme densities. So this is, temperature measured in MeV, that's mega electron volts, and that's a unit that nuclear physicists like. That's about 1 trillion Kelvin. And this is density measured in grams per centimeter cube. We think at the low densities and low temperatures, we know from laboratory experiments that the universe is made of nuclei, and if you go to higher densities, you get some neutrons out of these nuclei. And at the most extreme densities, the theory of quantum chromodynamics tells us that really what you're going to encounter are not nucleons, but quarks. And we expect this phase of matter to be an exotic state called a color superconductor, very much like an electron superconductor. All of this, almost everything except the very low density, low temperature stuff is the expectations of theoretical physics. We haven't really observed all of these phases in nature. And we expect that there will be a transition from matter containing hadrons, neutrons, protons, and everything else that we see in the laboratory to matter containing quarks and gluons at some high density and high temperature. And there's a transition region that we are trying to study both in the laboratory. But neutron stars provide a very interesting way of studying the very low temperature, high density part of the space diagram. This part of matter is interesting because it can contain very exotic structures. It can contain superfluids, solids, etc., unlike matter at very high temperature, which usually turns out to be simple in terms of its phase structure. So neutron stars give us an astrophysical probe of the properties in this part of the phase diagram, and that's why they remain very interesting. If you smash two neutron stars together, you can heat them up to high temperatures. And those sorts of collisions, I'll briefly mention them, we think will be able to allow us to study the phase diagram of matter at higher temperatures, because when you collide neutron stars, there's enough energy to create high temperatures. And the challenge for nuclear astrophysics is to go from observations to information about this phase diagram. So based on our understanding of nuclear physics and this phase diagram, over the last few decades, we've constructed what a canonical neutron star is supposed to look like. So typically, a neutron star has a mass of about 1.5 times the mass of the sun. The radius of the neutron star is a very important observable, and we think it could range from about 10 kilometers to, say, 14 kilometers. The canonical value is about 12 kilometers. The outer regions of the neutron star contain matter at relatively low density. So you can see that this is a 12-kilometer neutron star. At the very edge, which is called the outer crust, you have just ordinary nuclei, but the electrons that are running around between these nuclei are relativistic, unlike the electrons that are running around the solids that exist in this room. But you go down about 500 meters into the neutron star, and the density of matter is already increased from 10 to the 4 grams, which is something you can make in the laboratory, to 10 to the 11 grams per centimeter cubed. And then matter gets very interesting already. So in addition to nuclei and electrons, which is what we are familiar with, matter consists of nuclei. It's got a bunch of neutrons that are also freely floating around between nuclei. And we think that this phase of matter is both a solid and a superfluid because it's got this sea of neutrons between nuclei that form a superfluid. And if you go further down, if you go to about 2 kilometers deep into the neutron star, all of these nuclei get so close together that they merge, and the way they merge is very interesting. But eventually, what ends up happening is you form a liquid of just neutrons, protons, and electrons. And this part of the neutron star is actually very important from the structure point of view because it occupies a very large fraction of the neutron star's volume and makes up for most of the neutron star's mass. And this region, from about 10 to the 14 grams to about 6 to 10 to the 14 grams, we have the tools to describe this based on our knowledge of nuclear physics and the physics of nuclei. But at densities that are larger than 6 times 10 to the 14 grams, we no longer have the theoretical tools to describe what happens here. So we have a lot of models, a lot of speculation, but no reliable calculations of what happens. This is the region where nuclei and nucleons are slowly transforming into quarks, and we label this as the quark-hadron transition region. There are 2 things we know about it. Whatever makes up this must have quark degrees of freedom playing a role. And we know that they are strongly interacting with each other. And they are, that's why it's such a difficult problem to solve theoretically. And a description of this phase, either in terms of quarks or in terms of baryons, has been very elusive. And if you go to even higher densities, you can describe matter again because of a very interesting property of QCD called asymptotic freedom. And at the highest densities, perhaps we have a chance of describing matter using some of the tools that we already know in quantum chromodynamics. And it may be that such a phase exists where the description in terms of quarks that are superconducting actually holds. So I'm going to tell this story about trying to go from observations back to the neutron star interior in 2 parts. So we have this theoretical picture of what a neutron star is supposed to look like, but now we want to use observations to go and confirm that some of this model expectations are actually borne out. So let's start with the crust. I explained that the crust contained a solid outer region and a superfluid and solid inner region. And the story I'll tell you now is how we used observations to learn about the possible existence of a piece of the neutron star that's both solid and superfluid. And to understand that, we have to go back to neutron star observations and see an observation of a neutron star that's specifically sensitive to some properties of the crust of the neutron star. So when you have a neutron star in a binary, so this is a neutron star, here's a regular star, and matter from the regular star accretes onto the neutron star. So when matter from a companion falls onto the neutron star, it emits a bunch of X-rays because it comes in with a high velocity and eventually lands on the neutron star. It also ignites reactions inside the core, inside the crust of the neutron star. So this is the surface of the neutron star. As you go into the neutron star, you have different layers of different material. You have hydrogen and helium burning near the surface. Then if you go further down, you could have carbon burning. And then at some point, you go from the outer crust to the inner crust. So this is the region of the star where I was talking about there being both neutron superfluidity and nuclei as a solid. An interesting phenomena that occurs during accretion is that there are reactions that occur at a fairly deep layer inside the neutron star, and we can calculate the amount of energy that is being released deep inside the neutron star from our understanding of nuclear physics. When you release energy at that depth, it tends to heat up a part of the neutron star crust. So what nature is doing is basically producing this nice experiment where you have material, you heat the material, and then there's a mechanism by which you can stop the heating, and then you can go back and study how does this object cool.
And by burning here, you mean fusion.
This is, there are nuclear reactions that include fusion, but there are also other reactions that include just the capture of electrons. There's a whole bunch of different reactions that take place. We can calculate them to, a factor of 2 accuracy. That's why there's an uncertainty of 1 to 2 MeV of heat release there is. And the reason we think this is the underlying mechanism is because we have observed about 6 sources. Now we actually have 8 sources where you can watch this object that has just been heated by accretion, and accretion stops because in general, accretion is a episodic phenomena. It doesn't last for a long time. Accretion turns on, then it turns off. When accretion turns off, you can measure the X-rays from the surface of the neutron star and see this cooling of this hot crust. And the interesting observation is that the cooling timescale is measured in days. And even though the individual temperatures of these different neutron stars vary, the typical timescale for all of these neutron stars is in the 1,000-day timescale. So this 1,000-day timescale is telling us something about how heat is stored and transported inside the neutron star crust. And that's what we're going to use to learn what sort of material is in the neutron star crust. So again, going back to reminding you what's happening, you have a neutron star with a companion. The companion flows onto the neutron star. There's a lot of heat that is being generated, and that produces a large number of X-rays. And then it goes into a quiescent phase where the neutron star is just glowing and the matter is in a disk which is not falling onto the neutron star. And that's when the neutron star is cooling. And that's when X-ray measurements of neutron stars can provide a cooling curve. So if we ask, how do we model this cooling properties? It turns out that we need to know how is heat stored in the crust of the neutron star and how is heat transported in the neutron star. And to do that, we actually have to go back and ask ourselves, what are the thermal excitations in this high density matter? What happens to matter when you heat it up? When you heat matter up, there are 3 degrees of freedom that are actually playing a role in this exotic matter. One is there are these electrons, so you can heat up the electrons, just like you would heat up electrons here in a solid when you in a metal when you heat it up. Then there are these phonons, which are the oscillations of the lattice. But in addition, we have this new degree of freedom, which is very special to superfluids. This is called a superfluid phonon. And this is an oscillation of the superfluid. So all of these modes play a very important role in the thermal properties of this outer region of the neutron star. And over the last 10 years, we've developed a theory to understand how to describe all of these excitations. And there's a lot of interesting intricacies associated with this theory. For example, these phonons, which have to do with oscillations of the neutron, coupled with oscillations of the solid, and that produces interesting phenomena that are actually relevant for understanding heat conduction. But the bottom line is, when you're done with this theory, you find that this state of matter, which is both crystalline and superfluid, the conduction of heat by electrons is very high. But it does so even at a very small value of the heat capacity. And this is a very unique property. If you had an ordinary gas or if you had a liquid, usually what you end up having is you have a low conductivity and a high heat capacity, just the opposite of what you expect in a solid and a superfluid region. So if you were to stick either a gas or an ordinary liquid into the neutron star crust, you would end up with a timescale that is incompatible with observations. The 1,000-day timescale that we are seeing is very, very specific to having a very large heat conductivity and a small heat capacity. So if you're seeing a small cooling timescale, you want this number to be small and you want the thermal conductivity to be large. And we find that the only way to achieve that is to be in this phase of matter that is simultaneously superfluid and a solid. So here's an example of how you went from a theoretical expectation of what should be in this region of the neutron star, using observations to then deduce that in fact this is the only compatible space of matter that can exist at these densities. So this basically shows that we can confirm some of these theoretical expectations with observations. So please stop me and ask me questions at any time. Yes, please go ahead.
Yeah, I'm going. So is this superfluidity from pairs of neutrons that form Cooper pairs?
Exactly.
Motivate them?
Yeah. Right. So the fact that neutrons, which usually reside inside a nucleus, begin to drip out of nuclei at these high densities is the origin of the superfluidity. Neutrons attract each other, and this attraction is adequate to make Cooper pairs of neutrons, and the neutron Cooper pairs then act like a superfluid. They don't act like a gas. And that is something that is required to explain this transient behavior that we are seeing. And the superfluid nature of neutrons has other implications for phenomena known as glitches in neutron stars. So there's the whole concept of superfluid dynamics, which to some extent is studied by researchers here, both on the theory and the experimental side, which are experiments and theory done about laboratory systems, actually has important import for some of the things that we study here in astrophysics. Any other questions? Yes.
When you say that the inner part is solid and superfluid, you don't mean it's a super solid.
No.
It's separate parts.
They're separate parts that they are, but at very, very low energies, you cannot tell the difference between a supersolid and a solid superfluid because the excitations are very similar, but the microscopic mechanisms are different. Yes.
With this same model, can it be used to explain what an anti-glitch phenomenon?
Yeah, so explaining glitches starting from this model is significantly more complicated. This phenomena is simple to interpret because it's a thermal process. Glitches have to do with the dynamics of vortices and how vortices interact. So the short answer to your question is maybe, but we don't have a way of understanding glitches in terms of the superfluid from a first principles approach. Okay, so the second part of the talk is, now I told you that the interior of the neutron star contains very high density matter. And we want to learn something about the high density matter. So how does one go about learning interesting things about the high density matter? And what I'm going to tell you is that observations and their theoretical interpretation tell us that there must be a region of the neutron star where the speed of sound is becoming very large very quickly. Typically, there's a speed limit, which is the speed of light. So you cannot have sound waves in any material that is going faster than the speed of light. But it looks like the material inside the neutron star is approaching the speed limit very quickly in the outer core of the neutron star. And the evidence for it comes from trying to understand masses and radii of a neutron star. So for a long time, we've known that if theoretical nuclear physicists give an astrophysicist a curve that relates pressure and energy density, the astrophysicist can make a unique prediction for the mass and radius relationship of neutron stars. So it only relies on general relativity. So nuclear physicists supply pressure versus energy density, and you can calculate what the mass as a function of radius is. So you can produce a unique curve for every potential model for this equation of state, and there is this one-to-one correspondence between the pressure, energy density, and the mass radius. So for example, if you observe an object that has a small radius and a large maximum mass like the one shown by the yellow curve here, then it would require that somewhere in the neutron star, the pressure must increase very rapidly. So the rate of increase of pressure as a function of density is controlled by the features of the mass radius curve. Now, theoretical physicists have spent decades trying to compute this pressure energy density curve, which is usually called the equation of state of matter. And what we've done over the last 10 years or so is basically I first identify regions of density where we can do reliable calculations. So it turns out for densities that are less than a few times 10 to the 14 grams per centimeter cube, this is the outer core of the neutron star, the degrees of freedom of neutrons and protons, so we can do calculations. Then there's this region where you have the quark-hadron transition that I mentioned earlier, where we cannot do calculations, so we can speculate on what can exist here. And then if you go to very high densities, you can do calculations again, and this is the region where QCD, the theory of quarks and gluons, is perturbative. So we can, in principle, have an error estimate for each of these points where we can do reliable calculations. And what we don't know is this interesting region that exists inside the neutron star. But we know that the speed of sound, which is just the derivative of the pressure with respect to the energy density, has to be less than the speed of light. So measured in units of the speed of light, sound speed squared cannot be larger, the slope cannot be larger than 1. So this puts an upper bound on how much pressure you can have at these densities, even though you can't do any reliable calculations. So just using the fact that the speed of sound must be less than the speed of light, you get an upper boundary on the pressure energy density curve. Now we see in nature that neutron stars with masses close to 2 solar masses exist. So these very heavy neutron stars need a lot of pressure to stay alive. And the fact that you need a lot of pressure for heavier neutron stars gives you a lower bound on what the pressure should be, again, providing us guidance in the region where we cannot calculate. So even though we don't know what's going on from a theoretical perspective, there are these general bounds that the equation of state must obey in this intermediate region. So let me say a few words about why this error estimate is so important. Because these bounds here depend crucially on how big this error bar is. So a lot of work in the nuclear physics community goes into trying to understand and minimize the size of this error bar where we can do calculations. So the effort is called nuclear effective field theory. So what we want to do is we want to estimate the error in the calculation of the interaction energy of these neutrons and protons. And to do that, for about 50 years, we use models. And when you use a model for the nuclear interaction, an unfortunate consequence of that is you can't estimate error. So you can have model A, model B, but there's no way to tell what's the uncertainty associated with the model. Effective field theory is a way of taking the nuclear interaction, which is described by a Hamiltonian. The Hamiltonian just tells you what is the interaction between 2 neutrons, 3 neutrons, etc. And it organizes it in a very nice momentum expansion. So as long as the momenta of the neutrons and protons in the dense matter are less than some characteristic scale, we think this is the scale associated with about twice nuclear density, you can do an expansion which is the most general expansion. So it's not a model anymore, it's the most general expansion of the Hamiltonian, and you can make predictions by using just a few of these terms. And as you keep adding more and more terms, the error associated with any observable, like say the energy or the pressure, should decrease as you go to more and more terms. So if you see this trend where the error is decreasing, then you're in the regime of validity of the theory. And when you see that higher order terms begin to make large contributions, then you know this theory breaks down. So this error estimation that I showed you earlier has come from such analysis of the equation of state. So just to highlight a few recent calculations, there's a large number of young people in the nuclear theory community that are working on trying to estimate what is the error in the calculation of the energy as a function of density. So as you include more and more terms in this effective field theory Hamiltonian, you can see that as you go to higher orders, this is the leading order, this is the next to leading order, you see that the error bands are beginning to decrease. And these calculations are what these error bars are based on. And it's telling you that up to about twice nuclear density, these calculations seem reasonably reliable. And with collaborators in the last few years, Christian Drischler, who is now at Ohio State, we've done some calculations to figure out what the pressure is as a function of density. And these young people must take most of the credit for these curves that tell you how pressure and energy density go. And the error bar that I showed in the previous plot is just the size indicated by this large region here. Yeah. Now, we want to then use this to construct neutron stars using the same strategy that I mentioned earlier. So if I just use the equation of state that we can calculate, the mass radius curve that I want to construct ends at a very low mass, because the densities that I am accessing are too low to describe an entire neutron star. But I can use the most general extrapolation. I can then say at higher densities, the speed of sound equals the speed of light. So I can ask myself, what is the maximum radius I can make, given this upper bound on the pressure? And I can also use the lower bound on the pressure to use the calculation to define the lower bound. So given a calculation of low density nuclear material and the general constraints, you can then predict what the range of masses and radii should be, in spite of not knowing what's happening to matter at these higher densities. So these are model independent bounds on the radius and mass of neutron stars.
But are you using maximum pulsar mass constraint here?
Yeah, so this is the maximum pulsar mass constraint that says that you have to make at least a 2 solar mass neutron star. And suppose in the near future, somebody discovers a 2.6 solar mass neutron star, either through gravitational waves or some other technique, then you can see that the minimum radius has to move from this value to the value shown by the purple curve. What this means is that as future observations give us more massive neutron stars, the range of radii allowed for neutron stars will begin to shrink. So that would be the ideal circumstance where we will know what the mass radius of these neutron stars should be just from observations, even though we don't have a theoretical basis for the high density matter. So when you put all of this together, this is currently our expectation for the mass radius of neutron stars. These bounds have very specific error estimates associated with them. The dark curves are the 1 sigma, and the light curves are the light bands or the 2 sigma. And interestingly, the observations from GW 1708 for the radius of a typical 1.4 solar mass neutron star exists in this range. So at the moment, gravitational wave measurements of the neutron star radius, in fact, the tidal deformability, don't really give us new information in the sense that they're consistent with theoretical predictions. What we would like is for them to choose one over the other. X-ray observations are more difficult to interpret. So NICER is an X-ray satellite that also tries to measure the radius of a neutron star. Those measurements, this is a 1 sigma error bar, and there are systematic errors that are not understood. And then there is a more massive neutron star with about 2.1 solar masses, whose radius has been measured in 2 different ways. So at the moment, we have compatibility between theoretical expectations and neutron star radii and observations. But it's in the not so distant future, the expectation is that observations from gravitational wave astronomy will give us neutron star mass radius in this range, where the uncertainties are going to be less than 10% on the masses and of the order of a few percent on the radii. So this is what we're hoping for in about a decade or so for neutron star mass radius. Once you have this, then you'll have a very strong constraint on pressure as a function of energy density. But already to exist in this interval between 2 solar masses and much larger solar masses, a neutron star equation of state we find must satisfy a very interesting property. We find that to make a 2 solar mass neutron star, if I have an equation of state where the speed of sound varies smoothly from 0 to its limit at very high density, which is called the conformal limit, where the speed of sound goes to 1/3, a smooth curve, such as denoted by the red curve here, is incompatible with neutron star observations. So if I want to make masses of neutron stars that we are observing and radii of neutron stars that we are observing, a smooth variation of the speed of sound is basically not favored. Instead, what is favored is a very large increase in the speed of sound. We don't know to what extent this must increase rapidly, but we know that it must increase beyond this value of 1/3. The implication is that the speed of sound cannot be a monotonic function in dense matter. And that's an interesting new insight we derived from just using neutron star observations. What we don't know is whether there is a potential first order phase transition where the speed of sound increases rapidly and then goes to 0 at a phase transition and then rises again. So all of these possibilities exist, but there are some, simple monotonic functions of the speed of sound that have already been ruled out. Now, this is a great time to be studying neutron star masses and radii, because when you observe a neutron star binary through gravitational wave observations, you measure something known as the tidal deformability, which is the ability to change the shape of a neutron star by the external gravitational field. So when you bring two neutron stars close to each other, the companion will produce a quadrupole deformation on one of the neutron stars. And the extent to which you deform this neutron star is called the tidal deformability of the neutron star. And that's a very sensitive function of the radius. So the larger the tidal deformability, the larger is the neutron star radius. Now, this is the observable that we are going to get to measure better and better in the next decade, because gravitational wave astronomy is going to get us to the point where we will see many of these. And it's staggering to note that the next generation of gravitational wave detectors, which in the United States is called Cosmic Explorer, and which in Europe is called Einstein telescope, will take us from maybe 1 or 2 neutron star mergers a year to 100,000 neutron star mergers a year. So this is not a small, smooth transition in gravitational wave astronomy. This is a staggering revolution that is going to happen if they build a 3rd generation detector. And at that point, the error bar associated with tidal deformability measurements, which is now very large from GW 1708, the very first neutron star merger that we have. So again, these are the upper limits and the lower limits on the tidal deformability that I derived from just using theoretical considerations. This is the current constraint. But once you get to measuring tidal deformability at a % level, you're no longer going to have an important error. Instead, you will have in the mid-2030s with these new instruments, an actual constraint on the neutron star tidal deformability as a function of mass, which would have pretty much uniquely determined what the mass radius of a neutron star is. So to do this, we will need a large number of high signal to noise ratio events, but the best expectations are that that is feasible with the next generation gravitational detectors. So if you're interested in learning more about this, you should certainly go take a look at the science study that's published about the Cosmic Explorer and all of its scientific capabilities. What would be really exciting is if we find objects that are not in the neutron star window. So once you establish that neutron stars must lie on a certain plane, and you find this odd object that does not have the tidal deformability of a neutron star, then you're opening new parameter space. Now you're finding objects that does not belong to the typical baryon created objects in the universe. And that's when somebody buys a ticket and goes to Stockholm to collect the prize. But that is the discovery potential of this whole mission. When you see 100,000 neutron stars, there's a small chance, if these objects exist, that you will see some that don't fall in your neutron star window. And if they don't fall in the neutron star window, then you have to break the laws of physics to create these objects, and that's going to be pretty exciting. So the other exciting part is going to be just understanding what actually happens when 2 neutron stars collide. And that's an exciting problem. Many people here are working on this topic. And that has to do with the fact that the dynamics of very high density matter is very important to modeling neutron star mergers. So this is a beautiful movie that was made after the first neutron star merger by NASA. And what shows is the violent outcome of smashing 2 neutron stars together. It creates a gamma ray burst. It creates material that produces optical light, infrared light. Ultimately, we are going to see gravitational waves, and we are going to see electromagnetic waves from the collision of these neutron stars. And understanding them is going to rely on our physics of the high density matter, because this is really 2 neutron stars colliding into each other, and being able to simulate them using numerical relativity. So finding correlations between gravitational waves and electromagnetic emission in the next generation gravitational wave era is going to be a really fun time to be studying neutron stars. So in the last 5 minutes or so, let me tell you the last part of the story, which I alluded to. What if we find objects that are not neutron stars somehow, either using gravitational waves or otherwise? What does it tell us about dark matter? So these compact objects offer new ways to study dark matter. There's a huge experimental effort that is trying to measure dark matter in the laboratory. There are these detectors that are looking for putting limits on the cross-section of dark matter. There are astrophysics efforts trying to measure dark matter. So dark matter, trying to find new strategies to constrain or discover dark matter, especially its particle nature, is very important. And the reason neutron stars are good places to look for dark matter is because, one, they can accrete and trap dark matter. So the neutron star has a gravitational field. It's surrounded by dark matter. We know what the typical density of dark matter is. Just the fact that the dark matter encounters the neutron star when it's gravitationally attracted to it means that some fraction of them will get trapped by the gravity of the neutron star, and that will remain in the neutron star. And the amount of matter that you can trap in about a giga-year, that's a typical time scale for a neutron star lifetime. An old neutron star can have lifetimes of about a giga-year, is about 10 to the minus 14 solar masses. So that's a really tiny amount of mass, and you might say, how can we ever discover 10 to the minus 14 solar masses of dark matter in a neutron star? That's a solar mass, and I'll tell you how we can do that. And it also turns out that dark matter can be produced in a neutron star, because if dark matter has any coupling to baryons, then it's possible to produce dark matter by reactions that occur inside a neutron star. And if that is possible, then you can make a lot of dark matter. You can make a solar mass of dark matter by taking ordinary matter and converting it into dark matter. And finally, when a neutron star is born, or when neutron stars collide, they reach very high temperatures. And at very high temperatures, you have new reactions that can make dark matter. And if you can produce dark matter thermally, then you can produce about 0.1 solar mass of dark matter. So neutron stars can accrete and produce dark matter, and then we need to find a strategy to detect it. So the oldest idea dates back to the late 1980s, where Goldman and Nussanov realized that if dark matter is made of bosons that interact with each other very weakly, then even accreting 10 to the minus 14 solar masses of dark matter onto the neutron star can have catastrophic consequences. Because if you take 10 to the minus 14 solar masses of bosons and you compress it at the bottom of the neutron star, it wants to make a black hole. And once it makes a black hole, even though it's a tiny little black hole, it starts eating up the rest of the neutron star and eventually destroys the neutron star. So what these authors realized is if dark matter is bosonic, and it's weakly interacting, even 10 to the minus 18 solar masses of dark matter, which is typically of the size of, say, the mass of a regular neutron, is dangerous for a neutron star, because then it would just destroy the neutron star by forming a black hole. So the fact that you have neutron stars in the galaxy means that these types of dark matter candidates are already ruled out. They can't exist in nature, and that's how you can create an exclusion plot for dark matter. You can say that dark matter in this mass range from 10 to the minus 6 to about 10 GeV with these sorts of cross sections cannot exist. And experimentalists are also trying to explore the same phase space. So this is a very simple but robust constraint. Another way to study this is to say, okay, I want to convert a neutron star into a black hole. And one way to do that is to start with a regular neutron star surrounded by dark matter, and then let dark matter enter the neutron star, and it takes a certain amount of time for the black hole to form. The physical processes involved in forming the black hole and then devouring the rest of the neutron star is a very complicated process, and we are still trying to understand all of the physics that goes into it. But if this happens on the time scale of gigayears, then gravitational wave astronomy can again give us some insights into what's really going on here. Something has happened here. So let me skip over and get to this. So if it takes a long time to convert a neutron star into a black hole, then gravitational wave astronomy can again tell us something interesting about the population of neutron stars and black holes in the universe. And here's a calculation that was done by Divya Singh, a student at Penn State working with Satya Prakash, myself, and Emmanuel Berkey. And what she looked at was if it takes a long time to convert a neutron star into a black hole, what kind of populations does LIGO have to detect in terms of either detecting binary neutron stars or binary black holes? So if the neutron stars get converted to black holes, then the binary neutron star merger rate would decrease as a function of time. So the conversion time, if the conversion time is larger, then more neutron stars are left stable. So you should see as a larger neutron star fraction. The bottom line is, if you know what fraction of low mass objects lie in the neutron star or in the black hole region, then you can go back and ask yourself, is there an unusual process at hand that is converting neutron stars into black holes and then constrain dark matter that way? So the compact object zoo that you can create once you allow for new particles to exist is actually quite fascinating. So you could have neutron stars with an accumulation of dark matter in the core that is somehow stable because it's either fermions or it's got some repulsive interactions. You could create an object with a neutron star surrounded by a halo, and this halo is formed by the dark matter because we don't know much about the interactions of dark matter. If those interactions are repulsive, then it'll make the halo big. You could have objects that contain a sandwich of, a core of dark matter, a neutron star, and a halo. Or you could just have dark objects that have nothing to do with baryons. And the way we would discover this, as I alluded to earlier, is you would find that you are measuring objects in the universe that have masses that are less than 0.1 solar mass. And we have objects that have tidal deformabilities that don't quite fit in with the neutron star picture. So all of these provide a way of getting to the very exotic new object scenarios. So let me conclude by highlighting the main points here. What we are trying to unravel is use observations and theory to see what's inside the neutron stars. The first part of what I told you said that accreting neutron stars are really interesting thermal physics laboratories. They're telling us about the low temperature properties of solids and superfluids that exist inside the neutron star. In the second part of the talk, I said that to make massive neutron stars that are also quite compact, you need a very high speed of sound. And that's something we didn't know a few years ago. And that tells us something about the nature of very high density matter. And the fact that it's not a monotonically increasing function of density is a new insight. I think the correlation between gravitational waves and electromagnetic waves, when we see the next generation of neutron star mergers with new detectors, is going to be a really interesting era, because then we can study the dynamics of high density matter and its relevance for various multi-messenger observations. And the last part of the story had to do with using neutron stars as laboratories for dark matter. So thank you again for your patience.
Thanks, Sanjay, for a great talk. We have some questions.
I have a question that since we were talking about using the tidal deformability to constrain the equation of state, so that corresponds to the mass quadruple. What if for next generation detectors we start considering like the current quadruple or the mass quadruple? So will that make things better or worse for constraint?
I'm not really an expert on that, but my guess is that higher order contributions will become relevant much later in the signal, because the frequency, you'll have to go to higher frequencies to be sensitive to higher order moments in the deformation. So I would say that extracting limits on the quadrupole deformation or other deformations of the neutron stars that are tidally induced will have large errors associated with it, because that's pretty much going to happen when the neutron stars almost touch. So my thinking is that more than higher order terms, these dynamic times, the fact that even the quadrupole moment has a time dependence, will be complicated. But again, I suspect that'll be a less powerful tool on constraining the equation of state, simply because the uncertainties will be large. That's my guess, but I'm not an expert on that.
On that one, I think you're right. Basically, these will contribute to systematicness.
Okay.
You have to achieve precisions of number of percent on tidal deformability.
Right.
Due to quadrupole for this to kick in.
Okay.
Okay, the question I had was, I think this was, we are extrapolating from, work with Drishler et al. So you did this low density calculation, right?
Yeah.
And then, you're projecting that if, gravitational wave observatories, when you're measuring, you have a mass radius diagram, and then you're putting like, 10%, yeah. Errors, somewhere related to this, you had a.
The red dots are coming in.
Yes. Yeah, so suppose we are actually able to do exactly that kind of measurement with 10% in those cubes that show up.
Yeah.
Now if you actually go backwards, how will it constrain your low density physics?
Right, so if a very strong constraint on low density physics will require these highly precise measurements to be at the edge of the bounds. So if these start getting towards the edge of the bounds, then it becomes a problem, because then you have to change the error bar to get that going. If they fall in the 11 to 12 kilometer range, it's very unlikely that they will constrain the low density physics. Okay, so the tension with low density physics will begin to occur only if they are on the extreme ends. Unfortunately, the neutron star is most sensitive to the properties about twice nuclear density. Right, so that's that's a hard game to play.
Yeah, so I think theory will have to do some catching up if these.
Right. So there are some scenarios that would be very difficult to accommodate within theory, and that would be the most interesting ones to go after.
And we had one question online,
Yeah.
which was the lambda scale in the chiral perturbation theory. How much do we know about that and their bounds on that?
Right, so there are calculations by, again, I think Daniel Phillips, Christian Drishler, and others who looked at it, using very sophisticated Bayesian methods to extract what that scale is. And that seems to vary between 500 MeV and 600 MeV, sometimes even smaller numbers. So that in terms of density, it corresponds to around twice nuclear density. I should mention that this effective field theory that we are currently using is the best tool we have, but it's not perfect. It has intrinsic issues that we're all trying to work on, but that's for another talk. It's a good tool, but it is not like the standard model, or it's not like a hydrogen atom. There are conceptual questions that we still are grappling with, but it's the best we got at the moment.
All right, we should end. Thank you very much, Sanjay.